Welcome to Whispering Atom, where the gentlest wonders of our natural world unfold like secrets shared between old friends, and science becomes a peaceful companion for your journey toward rest. I'm so grateful you've chosen to join me tonight as we explore one of nature's most beautiful and contemplative phenomena, the appearance of rainbows after the softest, quietest storms, when the air is still settling and the light is just beginning to find its way through the last gentle drops of rain. As you settle in wherever you are in this wide world, I'd love to know where you're watching from tonight and what time it shows on your clock. Are you perhaps listening from a place where gentle rain sometimes visits your windows, where you've seen those perfect moments when a storm passes quietly and leaves behind the gift of colored light? Maybe you're somewhere dry where storms are rare but treasured, or perhaps you're in a place where rain is a constant, gentle companion. Take a moment, if you'd like, to share with us in the comments below where you are and what time your part of the world is experiencing right now. There's something wonderfully connecting about knowing we're all here together, sharing this moment under the same vast sky that holds all the storms and all the rainbows. Now, get comfortable. Let your breathing settle into its natural rhythm. Let your shoulders drop just a little. Perhaps adjust your pillow or pull that blanket a bit closer. Tonight, we're going to explore something magical that happens when the atmosphere is at its most gentle. When storms move through our skies with whispered rain rather than thunderous downpours, and when the conditions become just right for sunlight to paint arcs of color across the heavens. We'll discover why the quietest storms often give us the most perfect rainbows, and how this beautiful phenomenon connects us to some of the most elegant physics in the natural world. Imagine, if you will, that you're standing at a window on an afternoon when the weather has been soft and contemplative. Outside, a gentle rain has been falling for the past hour. Not the dramatic downpour of a thunderstorm, but the kind of quiet precipitation that seems to whisper rather than announce itself. The droplets touch the ground with barely a sound, creating tiny circles and puddles that appear and disappear like gentle thoughts on the surface of still water. This is the kind of storm that doesn't demand attention through thunder or lightning, doesn't announce its presence with dramatic winds or sheets of rain that blur the world into impressions. Instead, it settles over the landscape like a soft gray blanket, transforming familiar scenes into something slightly dreamlike, slightly subdued. The air smells clean and fresh, carrying that distinctive scent that comes when dust settles and the earth drinks slowly and peacefully. As you watch from your window, you notice that the rain is beginning to lighten, becoming even more gentle than it was before. Individual droplets become visible as they fall, each one catching what little light filters through the overcast sky. The clouds themselves seem to be taking on a different character, no longer the uniform gray that accompanied the rain, but showing hints of texture, suggestions of brightness behind the moisture. And then, in that perfect moment that seems to exist outside of ordinary time, something begins to shift in the western sky. The sun, which has been hidden behind the gray veil of clouds, finds a gap, not a dramatic break that floods the world with sudden brilliance, but a gentle opening that allows just enough light to slip through. This light has a quality that's different from the harsh brightness of full sunshine. It's soft, diffused by its passage through the moisture-laden air, carrying with it a warmth that feels like a gentle hand on your shoulder. The rain continues its quiet fall, but now each droplet becomes something more than just water descending from the sky. With the sun's gentle rays slanting through the air, every drop becomes a tiny prism, a microscopic lens that interacts with light in ways that follow some of the most beautiful laws of physics. You can't see this interaction yet. It's happening at a scale too small for human eyes to perceive directly, but the stage is being set for one of nature's most peaceful and spectacular displays. This is the moment when the conditions become perfect for what meteorologists and physicists call optimal rainbow formation. The air is filled with countless water droplets, each one a perfect sphere suspended in the atmosphere by the gentleness of the precipitation. The sun is positioned at just the right angle, low enough to create the geometry necessary for rainbow formation, but not so low that its light is completely blocked by the landscape. The background provided by the receding storm clouds creates the perfect canvas against which colors can be seen clearly. The quietness of this particular type of storm is crucial to what's about to unfold. In violent weather, raindrops are distorted by strong winds, blown into irregular shapes that scatter light unpredictably. Thunder and lightning create atmospheric disturbances that can disrupt the delicate conditions necessary for clear rainbow formation. But in this gentle precipitation, the droplets maintain their perfect spherical shapes, hanging in the air like countless tiny crystal balls, each one poised to work its optical magic. The temperature of the air during these quiet storms often creates ideal conditions for rainbow formation. The cooling effect of gentle rain brings the air to a temperature and humidity level where water droplets can maintain their shape and clarity without being buffeted by thermal currents or convective winds. The droplets fall slowly enough that they remain spherical, creating the precise optical geometry that transforms ordinary sunlight into bands of color. As you stand watching from your window, you might notice that the quality of light in the landscape has begun to change in subtle ways. Colors seem more saturated, more present than they did under the flat gray light of the storm. The green of grass appears deeper, the red of a distant roof more vivid. This enhancement of color is one of the first signs that the atmospheric conditions are becoming optimal for rainbow formation. The same properties of light and moisture that will soon create a rainbow are already beginning to affect how you perceive the ordinary colors of the world around you. The air has a particular clarity that comes only after gentle rain. Dust and pollen have been washed from the atmosphere without the violent mixing that characterizes thunderstorms. The result is air that's remarkably clean and transparent, allowing light to travel through it with minimal scattering or absorption. This clarity is essential for the crisp, clear rainbows that often follow quiet storms, creating conditions where colors can appear with startling purity and definition. You might notice that birds are beginning to emerge from their sheltered spots, their songs adding a gentle soundtrack to this peaceful transition from storm to clear skies. The quiet after gentle rain has a special quality. It's not the eerie silence that sometimes follows violent weather, but rather a soft, contemplative hush that seems to invite reflection and appreciation of subtle beauty. The droplets in the air are now at their most perfect for rainbow formation. They're small enough to remain suspended without falling too quickly, but large enough to interact effectively with light waves. Each droplet is a perfect sphere held in that shape by surface tension and the gentle dynamics of quiet precipitation. These spheres are nature's own precision optics, created not in laboratories, but in the peaceful interaction between water and air. As more sunlight begins to filter through the thinning clouds, you start to sense that something extraordinary is about to happen. The light has that special quality that seems to make everything glow softly, as if the world has been touched by a gentle enchantment. This is the light that has traveled 93 million miles from the sun, passed through Earth's atmosphere, and is now encountering countless perfect spheres of water suspended in the clean air. The angle of the sun is crucial at this moment for a rainbow to form. The sun must be behind you as you look toward the area where the rainbow will appear, and it must be positioned at less than 42 degrees above the horizon. In the gentle afternoon light following a quiet storm, these conditions often align perfectly, creating the geometric requirements for one of nature's most beautiful optical phenomena. The backdrop for the coming display is provided by the storm clouds that are beginning to move away. These clouds, darker than the brightening sky around them, will provide the perfect contrast against which a rainbow's colors can be seen clearly. Without this dark background, the delicate colors of a rainbow might be lost against a bright sky, invisible to human eyes despite being physically present in the scattered light. As you watch, you begin to notice something that seems almost too subtle to be real at first. A faint brightening in the air where the sun's rays are passing through the densest concentration of suspended water droplets. This brightening is the first sign that countless individual interactions between light and water are beginning to add up to something visible something magnificent. The physics happening at this moment is elegant in its simplicity, yet profound in its implications. Every droplet is acting as a tiny prism, bending the white light of the sun and separating it into its component colors. But more than that, each droplet is acting as a curved mirror, reflecting some of the light back toward you at very specific angles. The combination of these two effects, refraction and reflection, is creating conditions where light that enters the droplets as ordinary white sunlight emerges organized into the distinct colors that will soon paint an arc across the sky. The beauty of this process lies in its gentleness and precision. There's no violence here, no force or pressure, just the quiet interaction of light waves with water, following laws of physics that are as reliable as sunrise and as elegant as music. Each photon of light that enters a water droplet follows a path determined by its wavelength, with blue light bending at slightly different angles than green light, which bends differently from red light. This is why quiet storms produce such perfect rainbows. The gentle conditions allow each droplet to maintain its perfect spherical shape, creating the precise optical conditions necessary for clear color separation. The lack of wind and turbulence means that the droplets remain in stable positions long enough for the light interactions to produce a steady, visible result. The clear air washed clean by gentle rain provides the perfect medium for light to travel without interference. As you continue to watch from your window, you might notice that other people are beginning to step outside, drawn by the same subtle changes in light and atmosphere that have caught your attention. There's something about the moments following a quiet storm that invites contemplation and appreciation of natural beauty. The harsh edges of daily life seem softened, replaced by a gentle awareness of the extraordinary phenomena that surround us when conditions are just right. The suspended water droplets are now perfectly positioned to demonstrate one of the most beautiful examples of optical physics occurring in nature. Each droplet is a three-dimensional lens and mirror combined, capable of taking the full spectrum of solar radiation and organizing it into the distinct bands of color that human eyes can perceive as red, orange, yellow, green, blue, indigo, and violet. But the rainbow hasn't appeared yet. What you're witnessing is the quiet preparation, the gentle alignment of conditions that will soon produce one of nature's most peaceful and spectacular displays. The sun continues to find gaps in the thinning clouds. The last droplets of rain continue their gentle descent, and the air holds millions of perfect spheres of water, each one poised to play its part in the coming symphony of light and color. This is the magic of quiet storms. They create conditions where nature's most delicate and beautiful phenomena can unfold without disturbance. Unlike the dramatic weather that captures headlines and demands attention, these gentle transitions from rain to sunshine invite us to slow down, to notice, to appreciate the subtle beauty that emerges when the atmosphere is at its most peaceful and cooperative. As we prepare to explore exactly how these perfect conditions will soon transform into visible bands of color stretched across the sky, we can rest in the knowledge that we're witnessing one of the most reliable and beautiful processes in the natural world. The physics of rainbow formation has been operating unchanged for as long as there has been sunlight and rain on Earth, creating moments of wonder and beauty that connect us to the fundamental forces that govern light, water, and vision. In the chapters ahead, we'll discover exactly how this gentle interplay between light and water creates the rainbow that's about to grace the sky outside your window, and why the quietest storms so often give us the most perfect examples of this eternal dance between sunshine and rain. As we continue our peaceful observation from the window, watching the gentle transformation taking place in the sky above, it becomes important to understand what makes some storms whisper while others roar, and why this difference is so crucial to the formation of those perfect rainbows that appear when the atmosphere is at its most gentle and cooperative. The type of storm that has just passed over your landscape represents a particular kind of weather pattern, one that creates ideal conditions for optical phenomena precisely because of its restraint and gentleness. The storm that brought this soft rain to your window began its life perhaps hundreds of miles away, forming not through the violent collision of dramatically different air masses, but through the gradual, peaceful convergence of atmospheric conditions that favor gentle precipitation over dramatic displays. These quiet storms often develop when warm, moist air encounters cooler air in a slow, steady process that allows the atmosphere to reach equilibrium without the sudden pressure changes and temperature gradients that create thunderstorms and violent weather. The formation of gentle rain clouds follows a process that's almost meditative in its gradual progression. As warm air rises slowly through the atmosphere, it cools at a predictable rate, allowing water vapor to condense into droplets at a pace that permits the formation of stable, well-organized cloud structures. Unlike the towering cumulonimbus clouds that generate thunderstorms, these gentle rain clouds, often stratus or nimbostratus formations, develop in horizontal layers that spread across the sky like soft blankets. The temperature differences that drive these quiet storms are usually modest and gradual, creating atmospheric conditions that favor steady, gentle precipitation over the dramatic downpours associated with more violent weather. When air masses meet gently, without sharp boundaries or sudden changes, they create weather patterns that can persist for hours or even days, bringing the kind of steady, soaking rain that gardeners treasure and that creates perfect conditions for rainbow formation. The wind patterns associated with quiet storms are as gentle as the precipitation they produce. Instead of the swirling, chaotic air movements that characterize thunderstorms, these weather systems generate smooth, laminar flow patterns that keep raindrops in their perfect spherical shapes as they fall. Strong winds can distort raindrops, flattening them or breaking them apart in ways that interfere with the precise optical geometry needed for clear rainbow formation. But the gentle breezes that accompany quiet storms allow each raindrop to maintain its integrity as a perfect optical element. The pressure patterns that create quiet storms also contribute to their rainbow-producing potential. These weather systems typically involve gradual changes in atmospheric pressure rather than the sharp gradients that generate violent weather. The result is an atmosphere that remains stable and predictable, without the turbulence and convective activity that can disrupt the delicate conditions necessary for sustained rainbow visibility. As the gentle rain continues its quiet descent outside your window, each droplet follows a path determined by the calm air through which it falls. In violent storms, raindrops are buffeted by updrafts and downdrafts, blown sideways by strong winds, or shattered by collision with other droplets moving at different speeds. But in the peaceful precipitation of a quiet storm, each drop falls in a straight, unhurried path, maintaining its perfect spherical shape through surface tension and the gentle dynamics of its passage through still air. The size distribution of raindrops in quiet storms tends to be more uniform than in violent weather, another factor that contributes to optimal rainbow formation. When precipitation forms gradually and gently, droplets have time to reach similar sizes through the slow processes of condensation and coalescence. This uniformity creates conditions where light interacts consistently with the water droplets, producing the clear, well-defined colors that characterize the best rainbows. The electrical activity, or lack thereof, in quiet storms also plays a role in their rainbow-producing capabilities. Thunderstorms generate electrical charges that can affect the behavior of water droplets and create atmospheric disturbances that interfere with optical phenomena. But quiet storms typically develop without significant electrical activity, maintaining the stable atmospheric conditions that allow light to interact with water droplets in predictable, undisturbed ways. The duration of quiet storms often provides another advantage for rainbow formation. While violent thunderstorms may pass quickly, leaving little time for optimal conditions to develop, gentle storms often persist long enough for the perfect combination of factors to align. The extended period of steady precipitation saturates the air with uniformly sized droplets, creating a stable medium for light interaction that can persist as conditions gradually transition from storm to clearing skies. The transition period as a quiet storm ends is particularly important for rainbow formation. Unlike violent storms that can end abruptly, leaving behind chaotic atmospheric conditions, gentle storms typically fade gradually, allowing for a smooth transition from precipitation to clearing skies. This gradual change creates an extended period where water droplets remain suspended in the air while sunlight begins to penetrate through thinning clouds. The perfect recipe for rainbow formation. The cloud structures that generate quiet storms often have characteristics that enhance their rainbow-producing potential. The layered, stratiform clouds that typically produce gentle precipitation have relatively uniform density and moisture content, creating consistent conditions for light interaction as the sun begins to shine through them. When these clouds start to thin and break up, they often do so in ways that create the ideal backdrop for rainbow visibility. Dark enough to provide contrast, but not so dense as to block all sunlight. The geographic and topographic factors that favor quiet storms also tend to be those that create good conditions for rainbow observation. Gentle weather patterns often develop in areas with moderate topography and stable atmospheric conditions, creating the kind of landscapes where rainbows can be seen clearly against appropriate backgrounds. Mountains, valleys, and large bodies of water can all influence local weather patterns in ways that favor the development of gentle precipitation followed by clearing skies. The seasonal timing of quiet storms often coincides with atmospheric conditions that favor rainbow formation. Spring and autumn, when temperature differences are moderate and atmospheric patterns are transitioning between seasonal extremes, often provide the most frequent occurrences of gentle storms followed by ideal rainbow conditions. The angle of the sun during these seasons is also often optimal for rainbow formation, creating the geometric relationships necessary for clear visibility of the full spectrum. The humidity levels associated with quiet storms create another factor that favors rainbow formation. These weather systems typically develop in environments with moderate to high humidity, ensuring that plenty of moisture is available for droplet formation and suspension. The gradual saturation of the air during gentle precipitation creates conditions where droplets can remain suspended long enough for extended rainbow visibility, rather than falling quickly out of the zone where light interaction occurs. As you watch the gentle rain beginning to diminish outside your window, you're observing the final stages of this peaceful weather pattern. The droplets are becoming smaller and more widely spaced, but they're also becoming more uniform in size and shape as the violent mixing processes that characterize the height of any storm begin to calm. The air is clearing of the larger particles and debris that can interfere with optical phenomena, leaving behind the clean, transparent atmosphere that provides the perfect medium for light interaction. The barometric pressure is beginning to rise as the low-pressure system responsible for the storm moves away, creating the stable atmospheric conditions that favor sustained rainbow formation. The temperature and humidity are reaching the balance point where water droplets can remain suspended without being too dense or too sparse for optimal light interaction. The wind is calming to the gentle levels that allow droplets to maintain their spherical shapes while remaining positioned in the optimal zones for rainbow formation. The cloud cover is beginning to show the characteristic patterns that herald the end of gentle storms. Not the dramatic clearing that follows violent weather, but the gradual thinning and brightening that allows sunlight to begin penetrating the moisture-laden atmosphere. These clouds are becoming less uniform, developing gaps and thin spots that will soon allow focused beams of sunlight to interact with the suspended water droplets. The approaching end of this quiet storm represents the culmination of atmospheric processes that began hours ago and hundreds of miles away. All the factors that favor gentle precipitation, the gradual air mass boundaries, the moderate temperature differences, the stable pressure patterns, the lack of electrical activity, are now combining to create the ideal conditions for one of nature's most beautiful optical displays. The air outside your window is now filled with millions of perfect water droplets, each one a tiny sphere maintained in ideal shape by the gentle conditions of the quiet storm. These droplets are positioned at various distances and heights, creating a three-dimensional array of optical elements that will soon interact with sunlight to produce the layered, complex beauty of a complete rainbow. The stage is set, the atmospheric conditions are perfect, and the gentle transition from storm to sunshine is beginning to unfold. The The meteorological factors that created this quiet storm, the gradual pressure changes, the moderate temperature differences, the stable atmospheric layering, are the same factors that now favor the formation of a clear, vibrant rainbow. The restraint and gentleness that characterize the storm's development and duration are now providing the perfect conditions for the optical phenomena that will soon paint bands of color across the sky. As the last drops of gentle rain continue their unhurried descent outside your window, they carry with them the potential for beauty that exists whenever atmospheric conditions align in just the right way. Each droplet is a perfect optical instrument, created not through human engineering, but through the peaceful processes of atmospheric physics operating under ideal conditions. The quiet storm has done its work, bringing moisture to the earth and cleansing the air while creating the perfect conditions for the rainbow that is about to emerge. The gentleness that characterized every aspect of this weather pattern, from its formation to its precipitation to its gradual ending, has provided nature with the canvas and the tools necessary for one of its most spectacular artistic displays. In our next exploration, we'll discover exactly how these perfect water droplets, suspended in the clean air left behind by the quiet storm, begin to interact with the emerging sunlight to create the first stirrings of visible color in the sky above your peaceful window. As the gentle rain begins to taper to the softest of sprinkles outside your window, we enter one of the most crucial and beautiful phases of rainbow formation, the moment when countless water droplets, each one a perfect sphere of crystal clear water, begin to dance in the stillness of the post-storm air. These droplets, suspended between earth and sky, are about to become nature's own optical instruments, each one capable of transforming ordinary sunlight into something extraordinary. To truly appreciate what's happening in the air outside your window, we need to understand that every single raindrop is a marvel of physics and natural engineering. Each droplet maintains its perfect spherical shape through the invisible but powerful force of surface tension. That same force that allows insects to walk on water and creates the dome-like shape of dewdrops on morning grass. In the gentle conditions following a quiet storm, these spheres are as perfect as any lens crafted in a laboratory, but formed entirely through the peaceful interaction of water molecules with the air around them. The spherical shape of each droplet is maintained by the cohesive forces between water molecules, which create a kind of invisible skin around the droplet that pulls it into the most efficient shape possible, a perfect sphere. This shape is crucial for the optical phenomena we're about to witness, because only a sphere provides the precise geometric relationships necessary for the refraction and reflection of light that creates rainbow colors. Any distortion in the droplet's shape would scatter light unpredictably, destroying the organized color patterns that make rainbows so beautiful and distinct. In the calm air following our quiet storm, these droplets exist in a state of perfect balance. They're large enough to interact effectively with light waves, but small enough to remain suspended in the air rather than falling rapidly to the ground. The gentle air currents that follow quiet precipitation create just enough movement to keep the droplets airborne, without the turbulence that would distort their shapes or scatter them chaotically through the atmosphere. Each droplet is also remarkably pure, containing nothing but water molecules arranged in the simple but elegant structure that gives water its unique properties. The gentle rain that created these droplets has washed the air clean of dust, pollen, and other particles that might interfere with the clear optical interactions necessary for rainbow formation. This purity means that light can pass through each droplet with minimal absorption or scattering, preserving the intensity and clarity that will soon become visible as bands of color. The size distribution of these post-storm droplets is particularly important for rainbow formation. In violent weather, raindrops can vary dramatically in size, from tiny mist particles to large drops that are flattened by air resistance or broken apart by turbulence. But in the gentle conditions we're observing, the droplets tend to be remarkably uniform in size, typically ranging from about 0.5 to 2 millimeters in diameter. The optimal range for interacting with visible light waves to produce clear, distinct colors. As you watch from your window, You might notice that these suspended droplets catch the light in subtle ways, creating tiny sparkles and glints as they move gently through the air. Each sparkle represents a droplet that's oriented at just the right angle to reflect light directly toward your eyes, giving you a preview of the optical magic that's about to unfold on a much larger scale. These individual interactions between light and water are like single notes in a symphony that will soon crescendo into the full harmonic beauty of a complete rainbow. The temperature of these droplets is also crucial to their optical properties. In the moderate conditions that follow quiet storms, the water remains in its liquid state, maintaining the smooth, continuous surface that's necessary for clear refraction and reflection. If the droplets were too cold, they might freeze into ice crystals with different optical properties. If they were too warm, they might evaporate too quickly to maintain stable positions for rainbow formation. But in the gentle temperature range of our post-storm environment, they exist in the perfect state for optical phenomena. The density of droplets in the air following a quiet storm creates another optimal condition for rainbow formation. There are enough droplets to provide continuous interaction with sunlight across a wide area of sky, but not so many that they interfere with each other or create a fog-like condition that would scatter light chaotically. This balanced density allows each droplet to act as an individual optical element while contributing to the collective effect that creates a visible rainbow arc. The positioning of these droplets in three-dimensional space is constantly shifting as they move gently through the air, but in ways that maintain the overall geometric relationships necessary for rainbow visibility. Unlike the chaotic motion that characterizes droplets in violent weather, the movement of post-storm droplets follows gentle, predictable patterns that preserve the optical conditions necessary for sustained rainbow formation. Each droplet may drift slowly through the air, but it maintains its essential relationship to the sun, to your viewing position, and to the other droplets around it. The electromagnetic properties of these water droplets make them perfect natural prisms and mirrors. Water has specific optical properties, its refractive index, reflectivity, and transparency, that are ideally suited for separating white light into its component colors. The refractive index of water is approximately 1.33, which means that light slows down and bends when it enters a water droplet, but in precisely the amounts needed to separate different colors by different amounts. As sunlight begins to penetrate the thinning clouds and reach these suspended droplets, each sphere becomes a miniature optical laboratory where the fundamental physics of light interaction with matter begins to unfold. When a beam of white sunlight encounters a water droplet, several things happen simultaneously, each following the precise laws of optics that have remained constant since light first began shining on water billions of years ago. Some of the light bounces off the droplet's surface without entering it, creating a reflection that follows the simple law that the angle of incidence equals the angle of reflection. But most of the sunlight enters the droplet, and this is where the magic of color separation begins. As the light crosses from air into water, it slows down and bends, a process called refraction, and different colors bend by slightly different amounts because they have different wavelengths. Inside each droplet, the separated colors travel through the pure water until they reach the back surface of the sphere. Here, some of the light exits the droplet and continues on its way, but a significant portion reflects off the inside surface of the droplet and travels back through the water toward the front. This internal reflection is crucial to rainbow formation because it sends the color-separated light back in the direction it came from, but at specific angles that depend on the wavelength of each color. When this internally reflected light reaches the front surface of the droplet again, it exits back into the air, but now it's been both separated into its component colors and redirected at precise angles. The geometry of the sphere ensures that each color emerges at a specific angle relative to the original direction of the incoming sunlight. Red light emerges at one angle, orange at a slightly different angle, yellow at another, and so on through the spectrum to violet. The remarkable thing about this process is that it happens in exactly the same way in every droplet that's properly positioned relative to the sun and your viewing angle. Millions of droplets, each acting as an individual optical instrument, all perform the same precise separation and redirection of light. The result is that light of each specific color is concentrated in particular directions, creating the organized bands of color that will soon become visible as a rainbow. The timing of this optical interaction is perfect in the gentle conditions following our quiet storm. The droplets remain in position long enough for the light interactions to be sustained rather than flickering, creating the steady, stable rainbow colors that characterize the best displays. The lack of turbulence means that the geometric relationships between sun, droplets, and observer remain consistent, allowing the rainbow to maintain its shape and intensity. Each droplet contributes its own tiny portion to the overall rainbow, but no single droplet creates all the colors you see. Instead, each droplet contributes primarily one color to the rainbow you observe, depending on its position relative to your viewing angle and the sun. The droplets that contribute red light to your rainbow are at slightly different positions than those that contribute blue light, creating the spatial separation that allows you to see the colors as distinct bands rather than a confused mixture. The three-dimensional nature of this droplet array means that the rainbow you see is actually a cross-section of a complete circle of colored light. The droplets that create your rainbow exist on the surface of an imaginary cone, with your eye at the apex and the rainbow arc marking where this cone intersects the curtain of suspended droplets. If conditions were perfect and the ground didn't interfere, you would see this complete circle, but usually we see only the arc that appears above the horizon. The purity of the water in these post-storm droplets ensures that the colors produced are clear and distinct rather than muddy or washed out. Any impurities in the water would absorb certain wavelengths of light, dulling the colors and reducing the clarity of the rainbow. But the distilled nature of rainwater, especially after gentle precipitation that doesn't stir up dust and debris, creates optical conditions that are as pure as any laboratory could provide. The stability of these droplets in the post-storm air means that the rainbow, once it appears, can persist for extended periods, sometimes for half an hour or more in ideal conditions. Unlike the brief, flickering rainbows that might appear during variable weather conditions, the rainbow that emerges from quiet storm conditions can provide a sustained display of color that allows careful observation and appreciation of all its subtle features. As you continue watching from your window, more sunlight begins to break through the clouds, illuminating more of the suspended droplets and setting the stage for the moment when enough light interacts with enough properly positioned droplets to create the threshold of visibility. The individual sparkles and glints you've been observing are about to combine into something much larger and more spectacular. The organized display of color that will soon arch across the sky. The droplets continue their gentle dance in the stillness, each one maintaining its perfect spherical shape, each one positioned to play its part in the coming display. The air remains clean and clear, washed by the gentle rain and calmed by the peaceful conclusion of the storm. The stage is set for one of nature's most beautiful demonstrations of how simple physical laws, operating through countless individual interactions, can create phenomena of breathtaking beauty and mathematical precision. In our next exploration, we'll discover how the sunlight that's beginning to reach these perfect droplets carries within it all the colors of the rainbow, hidden in what appears to be simple white light, waiting for the right conditions to reveal the spectacular diversity that has been there all along. As the sunlight grows stronger through the clearing clouds outside your window, beginning to illuminate the countless perfect droplets suspended in the post-storm air, we witness the first magical moments when invisible becomes visible, when the hidden spectrum within ordinary white light begins to reveal itself through the gentle alchemy of water and illumination. This is the moment when physics becomes poetry, when the mathematical precision of optical laws transforms into the visual beauty that has inspired wonder and contemplation for as long as humans have watched the sky. The light that's now beginning to reach the water droplets has traveled an extraordinary journey to arrive at this moment. It began its existence in the nuclear fusion reactions at the core of our sun, where hydrogen atoms combine under unimaginable pressure and temperature to create helium and release enormous amounts of energy in the form of electromagnetic radiation. This energy takes thousands of years to work its way from the sun's core to its surface, and then just over 8 minutes to cross the 93 million miles of space between the sun and Earth. When this sunlight reaches Earth's atmosphere, it appears to our eyes as white light, a seemingly uniform illumination that we've become so accustomed to that we rarely consider its true nature. But this white light is actually one of the most complex and beautiful phenomena in physics, containing within it every color that human eyes can perceive, all traveling together in perfect harmony until something separates them and reveals their individual identities. The white light approaching the water droplets outside your window is actually a mixture of electromagnetic waves of many different wavelengths, each corresponding to a different color that our eyes and brain interpret as part of the visible spectrum. These waves travel together at the speed of light, maintaining their individual characteristics while creating the combined effect that we perceive as white illumination. It's like a symphony where many different instruments play notes of different frequencies simultaneously, creating a harmony that contains all the individual melodies within it. The electromagnetic spectrum extends far beyond what human eyes can see, including radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. But the portion that concerns us for rainbow formation is the relatively narrow band of wavelengths that our eyes have evolved to detect, from about 380 nanometers for violet light to about 700 nanometers for red light. Within this range, every small change in wavelength corresponds to a slightly different color that our visual system can distinguish. Red light, at the longer wavelength end of the visible spectrum, has waves that are nearly twice as long as those of violet light at the shorter end. Orange, yellow, green, blue, and indigo fall between these extremes, each with its own characteristic wavelength that determines how it will behave when it encounters matter like the water droplets suspended in the air. These wavelength differences seem small when measured in nanometers, but they're large enough to create dramatically different optical behaviors that make rainbow formation possible. As the first strong rays of sunlight begin to encounter the water droplets outside your window, each photon of light carries its wavelength like a signature that determines how it will interact with the water. The physical properties of water, its density, its molecular structure, its electromagnetic characteristics, affect different wavelengths of light in subtly different ways, and these subtle differences are what allow the water droplets to act as prisms that separate white light into its component colors. When light travels from one medium to another, from air into water, for example, it changes speed, and this change in speed causes it to bend or refract. The amount of bending depends on both the properties of the materials involved and the wavelength of the light. This wavelength-dependent refraction is called dispersion, and it's the fundamental physical process that makes rainbow formation possible. In the water droplets suspended outside your window, red light with its longer wavelength bends less than blue light with its shorter wavelength when it enters the water from air. This difference in bending angles means that after passing through a water droplet, red and blue light travel in slightly different directions. When this happens to all the wavelengths present in white light simultaneously, the result is a spread of colors. The same white light that entered the droplet is separated into a fan of distinct colors as it emerges. The beauty of this process lies in its absolute consistency and precision. Every red photon that encounters a water droplet under the same conditions will bend by exactly the same amount. Every blue photon will bend by its own specific amount. The laws of optics operate with mathematical precision, ensuring that the color separation process produces consistent, predictable results that create the ordered bands of color we see in rainbows. But the interaction between light and water droplets involves more than just refraction. When light reaches the back surface of a spherical water droplet, some of it exits the droplet immediately, but a significant portion undergoes total internal reflection. It bounces off the inside surface of the droplet and travels back through the water toward the front surface. This internal reflection is crucial to rainbow formation because it concentrates the separated colors and directs them back toward the observer at specific angles. The combination of refraction upon entering the droplet, internal reflection at the back surface, and refraction again upon exiting the droplet creates a complex but predictable path for each wavelength of light. The geometry of these paths is what determines the specific angles at which different colors emerge from the droplet, and these angles are what create the organized structure of rainbow colors that appears in the sky. As more sunlight begins to illuminate the droplets outside your window, you might start to notice the very first hints of color beginning to appear in the air. These initial stirrings of visible color often manifest as subtle changes in the quality of light reflected from the suspended droplets. Perhaps a faint reddish tinge in one area, a slight blue-green cast in another. These early manifestations are individual droplets beginning to separate white light into its components, but not yet in sufficient numbers or organization to create the full rainbow arc. The threshold between invisible and visible rainbow formation is one of the most magical moments in optical phenomena. It represents the point where enough properly positioned droplets are interacting with enough sunlight to create sufficient color separation and concentration to exceed the sensitivity threshold of human vision. Below this threshold, the color separation is happening but remains invisible to our eyes. Above it, the rainbow suddenly becomes apparent as a coherent, organized display of spectral colors. The human eye is remarkably sensitive to color differences, capable of distinguishing millions of subtle variations in hue, saturation, and brightness. But even this sophisticated visual system requires a certain minimum intensity and organization of colored light before it can perceive rainbow colors as distinct from the background illumination. The droplets outside your window are approaching this threshold as more sunlight reaches them, and more individual color separation events begin to add up to a visible total. The angular precision required for rainbow visibility is extraordinary. For you to see a rainbow from your window, the sun must be behind you at an elevation of less than 42 degrees above the horizon. The water droplets must be in front of you at the correct distance and density, and the geometric relationship between these elements must be maintained with remarkable precision. A change of just a few degrees in any of these relationships can make the difference between a brilliant rainbow and no visible colors at all. The colors that are beginning to stir in the droplets outside your window each have their own story and character. Red light, carrying the least energy per photon but bending the least as it passes through water, will eventually form the outermost band of the rainbow arc. Its longer wavelength makes it less susceptible to scattering by small particles, allowing it to travel farther through the atmosphere and often appear more vibrant in the clear air following gentle storms. Orange light, with slightly shorter wavelengths than red, bends a bit more as it passes through water droplets and will form the next band inward from red. Yellow light bends more still, followed by green, blue, indigo, and violet, each taking its designated place in the spectrum according to the precise physics of wavelength-dependent refraction. The order of these colors in a rainbow is not arbitrary, but follows directly from the fundamental properties of light and water. Green light occupies a special position in the rainbow spectrum because it's near the peak sensitivity of human vision. Our eyes evolved to be most sensitive to the wavelengths of light that are most abundant in sunlight after it passes through Earth's atmosphere, and green light falls right in this optimal range. This enhanced sensitivity to green often makes it one of the most prominent and noticeable colors in rainbow displays. Blue and violet light, with their shorter wavelengths and higher energy per photon, interact most strongly with water molecules and undergo the greatest amount of bending as they pass through droplets. This strong interaction means that blue and violet light are efficiently separated from white light, but it also means they're more susceptible to scattering by atmospheric particles. In the clean air following gentle storms, however, this scattering is minimized, allowing the blues and violets to appear with exceptional clarity and intensity. The transition from white light to separated colors happens continuously as more droplets become illuminated and more light interactions occur. There's no single moment when the rainbow turns on, but rather a gradual building of color intensity and organization as conditions improve and more of the suspended droplet array becomes involved in the optical processes. This gradual emergence is part of what makes rainbows so captivating. They seem to materialize slowly from the air itself, growing stronger and more defined as you watch. The droplets that contribute to the emerging rainbow aren't randomly distributed throughout the air, but exist in specific zones where the geometric requirements for rainbow formation are met. These zones form surfaces in three-dimensional space, imaginary boundaries where droplets are positioned at exactly the right angles relative to the sun and your viewing position to create each color of the spectrum. As more droplets within these zones become illuminated, the rainbow becomes more complete and more visible. The pure water in these post-storm droplets ensures that the emerging colors are as clear and saturated as possible. Any impurities in the water would absorb certain wavelengths preferentially, dulling the colors and reducing the contrast between different spectral bands. But rainwater is naturally distilled, and the gentle precipitation of quiet storms doesn't stir up contaminants that might affect optical clarity. The result is color separation of laboratory-quality precision occurring naturally in the atmosphere. As you continue watching from your window, the strengthening sunlight illuminates more and more of the droplet array, and the first hints of organized color begin to appear in the sky. You might notice a faint reddish glow beginning to form in one area, or a suggestion of blue-green in another. These are the first stirrings of the full rainbow that's about to emerge. Individual colors beginning to organize themselves according to the precise laws of optics that govern how light and water interact. The mathematical beauty of what's happening outside your window would have delighted Newton, who first demonstrated that white light could be separated into colors using a glass prism and then recombined into white light again. But nature's version of this experiment, using millions of perfect water droplets instead of a single piece of glass, creates effects that are far more complex and beautiful than any laboratory demonstration. Each droplet acts as both a prism and a curved mirror, not only separating white light into colors, but also concentrating those colors and directing them at specific angles. The spherical shape of the droplets creates focusing effects that enhance the intensity of the separated colors, while the precise geometry of internal reflection ensures that the colors are sent back toward observers at the optimal angles for visibility. The emerging rainbow represents the culmination of countless individual optical events, each one following the same physical laws, each one contributing its small part to the magnificent whole. As we prepare to explore how these individual color contributions combine and organize themselves into the structured bands of the complete rainbow, we can appreciate that we're witnessing one of the most beautiful examples of emergent complexity in nature. Simple physical laws operating through countless individual interactions to create a phenomenon of breathtaking beauty and mathematical elegance. In our next exploration, we'll delve deeper into the hidden symphony of colors within sunlight, discovering how each wavelength carries its own character and story, and how the gentle precision of water droplet optics reveals these individual voices that normally sing together in the chorus of white light. As the sunlight streaming through the clearing clouds outside your window grows stronger and more focused, we have the opportunity to explore one of the most remarkable secrets of our universe. The fact that what appears to be simple, uniform white light is actually a complex symphony of electromagnetic radiation, with each wavelength carrying its own unique character, its own story, and its own role in the spectacular display of color that's about to unfold across the sky. To truly appreciate the rainbow that's forming outside your window, we need to understand that sunlight is not a single thing, but rather a harmonious blend of countless different wavelengths of electromagnetic radiation, each one distinct yet contributing to the unified experience we call daylight. It's like listening to a symphony orchestra where individual instruments play different notes at different frequencies, but the combined effect creates a rich, complex harmony that our ears perceive as unified music. The electromagnetic spectrum that emanates from our sun extends far beyond what human eyes can detect, stretching from radio waves with wavelengths measured in kilometers down to gamma rays with wavelengths smaller than the nucleus of an atom. Within this vast spectrum, the portion that our eyes have evolved to see occupies just a tiny slice. The visible light that spans from the deep red at about 700 nanometers down to the violet at about 380 nanometers. But within this narrow window lies all the color that enriches our visual world. Each wavelength of light within this visible spectrum has its own personality, its own way of interacting with matter, and its own story to tell about the nature of electromagnetic radiation. Red light, with its longer wavelengths, carries less energy per photon, but has remarkable staying power, able to travel farther through the atmosphere and penetrate deeper into water than its shorter wavelength cousins. This is why sunsets often appear red. The red wavelengths can survive the long journey through Earth's atmosphere when the sun is low on the horizon, while shorter wavelengths are scattered away. Orange light occupies a middle ground between the robust reds and the energetic yellows, carrying moderate energy per photon and moderate penetrating power. In the spectrum of sunlight, orange wavelengths contribute significantly to the warm, golden quality of direct sunshine, especially during the morning and evening hours when the sun's rays pass through more atmosphere and the shorter wavelengths are filtered out by scattering. Yellow light holds a special place in the solar spectrum because it's near the peak of the sun's energy output. Our star produces more energy in the yellow-green portion of the spectrum than in any other visible wavelength, which is one reason why human eyes evolved to be most sensitive to this range. Yellow light strikes a balance between energy per photon and atmospheric transmission, making it both abundant in sunlight and efficient at reaching Earth's surface. Green light, at wavelengths around 500 to 550 nanometers, represents the peak sensitivity range of human vision. This isn't coincidental. Our eyes evolved under sunlight, and natural selection favored visual systems that were most sensitive to the wavelengths that were most abundant and useful in our natural environment. Green light also interacts with water in ways that make it particularly important for rainbow formation, bending at angles that place it prominently in the center of the rainbow spectrum. Blue light, with its shorter wavelengths and higher energy per photon, has a much more dynamic relationship with Earth's atmosphere than longer wavelengths. Blue light is scattered strongly by the small molecules that make up air, which is why our sky appears blue on clear days. This same scattering tendency means that blue light in sunlight has often been scattered multiple times before reaching the water droplets outside your window, giving it a quality that's different from the more direct transmission of longer wavelengths. Indigo and violet light, at the short wavelength end of the visible spectrum, carry the highest energy per photon of any visible light. These wavelengths interact strongly with matter, are easily absorbed by many substances, and are scattered efficiently by atmospheric particles in the clean air following a gentle storm. However, violet and indigo light can appear with remarkable intensity and purity, creating the striking purple edge that caps the most vivid rainbows. The intensity distribution of these wavelengths in sunlight follows what physicists call a blackbody spectrum, the characteristic pattern of electromagnetic radiation emitted by any object based on its temperature. The sun, with a surface temperature of about 5,778 Kelvin, produces a spectrum that peaks in the yellow-green range, but includes significant energy across all visible wavelengths. This broad, smooth distribution of energy across the visible spectrum is what makes sunlight such an ideal source for rainbow formation. When this complex mixture of wavelengths reaches the water droplets suspended in the air outside your window, each wavelength begins its own individual journey through the optical processes of refraction, reflection, and dispersion. The remarkable thing is that each wavelength behaves according to the same physical laws, but because their wavelengths are different, they interact with water in subtly different ways that allow them to be separated and revealed as individual colors. The refractive index of water, the measure of how much light bends when it enters water from air, varies slightly with wavelength. For red light, water has a refractive index of about 1.331, while for violet light, it's about 1.344. These differences seem small, but they're large enough to create measurably different bending angles when light enters and exits water droplets. Over the path that light travels through a spherical droplet, these small differences in bending accumulate into significant differences in exit angles. When red light enters a water droplet, it slows down and bends according to its specific refractive index, travels through the water to the back of the sphere, reflects off the inside surface, travels back through the water, and exits at an angle that's determined by the cumulative effect of all these interactions. Violet light, with its different refractive index, follows a similar path but exits at a measurably different angle. The difference between these exit angles is what creates the spatial separation of colors that makes rainbow formation possible. The chromatic dispersion that occurs in water droplets is remarkably efficient at separating the components of white light. A single droplet can take a beam of white sunlight and spread it into a fan of colors spanning several degrees of angle. When millions of droplets all perform this same separation simultaneously, the result is an organized display of color bands that can stretch across a significant portion of the sky. But the story of each wavelength doesn't end with its separation from white light. Once separated, each color must travel through the atmosphere to reach your eyes, and this journey affects different wavelengths in different ways. The clean air following a gentle storm provides ideal conditions for this transmission, with minimal scattering, absorption, or other interference that might degrade the clarity and saturation of the colors. The psychological and physiological aspects of color perception add another layer to the symphony of wavelengths that creates rainbow beauty. Human color vision involves 3 types of cone cells in the retina, each most sensitive to different portions of the spectrum. The interaction between the wavelengths separated by water droplets and the response characteristics of these cone cells creates the rich, varied color experience that makes rainbows so visually compelling. The cultural and emotional associations that humans have developed with different colors also contribute to the impact of rainbow displays. Red light often evokes feelings of warmth and energy. Blue suggests coolness and calm. Green implies natural growth and harmony. These associations, developed through millions of years of evolution and thousands of years of culture, add emotional depth to the optical phenomenon unfolding outside your window. The temporal behavior of different wavelengths in rainbow formation reveals another aspect of their individual characters. As atmospheric conditions change, as droplet sizes shift, as the sun's angle changes, as the density of suspended water varies, different colors may appear and disappear at different rates. Red and yellow, being less sensitive to atmospheric variations, often persist longer than blue and violet, which can fade quickly when conditions become less than optimal. The polarization properties of different wavelengths also play a role in rainbow formation and visibility. Light reflected from the back surface of water droplets becomes partially polarized, and this polarization affects different colors differently. The result is that rainbow colors often have a distinctive quality that's different from ordinary reflected or transmitted light, a clarity and saturation that seems to make the colors glow with their own inner light. The quantum mechanical nature of light adds yet another dimension to understanding the wavelength symphony in sunlight. Each wavelength corresponds to photons with specific energy levels, and these energy differences affect how the light interacts with matter at the molecular level. In water droplets, these quantum effects influence the efficiency of various optical processes and contribute to the precise wavelength-dependent behaviors that make rainbow formation possible. As the sunlight streaming through the clouds outside your window continues to strengthen and reach more of the suspended water droplets, each wavelength begins to reveal its individual contribution to the emerging display. You might notice that certain colors appear more readily than others, perhaps the yellows and greens becoming visible before the reds and blues, or the warmer colors dominating the initial stages of rainbow formation. This differential appearance of colors reflects the complex interplay between the sun's energy distribution, the optical properties of water droplets, the transmission characteristics of the atmosphere, and the sensitivity characteristics of human vision. Each factor affects different wavelengths differently, creating a dynamic process where the rainbow builds and develops as conditions continue to optimize for full spectrum visibility. The coherence of the emerging rainbow, the way all these individual wavelength contributions combine into an organized, structured display, represents one of the most beautiful examples of emergent complexity in optical physics. Millions of water droplets, each separating white light according to the same physical laws, create individual contributions that add up to a phenomenon that's far more beautiful and structured than the sum of its parts. The bandwidth of each color in the emerging rainbow reflects the continuous nature of the electromagnetic spectrum. There are no sharp boundaries between red and orange or between blue and green. Instead, each color blends smoothly into its neighbors, creating the seamless progression of hues that characterizes natural rainbow displays. This smooth blending reflects the fact that sunlight contains not just the primary colors, but all the intermediate wavelengths between them. The saturation and intensity of each color in the developing rainbow depend on multiple factors. The energy content of each wavelength in the original sunlight, the efficiency of separation and concentration by water droplets, the transmission characteristics of the atmosphere, and the sensitivity of human vision to each wavelength. The interplay of these factors creates the unique color balance that characterizes each rainbow display. As you continue watching the emerging rainbow from your window, you're witnessing the individual voices and sunlight's hidden symphony beginning to separate and make themselves known. Each wavelength is telling its own story about electromagnetic radiation, about the physics of light and water, about the evolution of human vision, and about the mathematical beauty that underlies natural phenomena. The rainbow that's forming outside your window represents the temporary revelation of complexity that's always present in sunlight, but usually hidden from view. The gentle storm has created the perfect conditions for this revelation. The clean air, the perfect droplets, the optimal illumination, allowing you to see the individual components of what normally appears as unified white light. In our next exploration, we'll discover how the perfect spherical shape of raindrops creates the precise geometric relationships necessary for organizing these separated wavelengths into the structured, beautiful display that's about to arch across the sky outside your peaceful window. As we continue our gentle observation of the rainbow forming outside your window, we arrive at one of the most elegant and fundamental aspects of this natural phenomenon: the remarkable way that the perfect spherical shape of each water droplet creates exactly the right geometric conditions for transforming the separated wavelengths of sunlight into the organized, structured display of colors that will soon arch across the sky. The sphere, in its mathematical perfection and natural simplicity, holds secrets that make rainbow formation not just possible, but inevitable under the right conditions. To understand why the spherical shape is so crucial to rainbow formation, we need to appreciate that geometry and optics are intimately connected. The path that light takes through any transparent object depends entirely on the shape of that object's surfaces, the angles at which light enters and exits, the curvature of the boundaries between materials, and the internal reflections that occur within the object. In the case of water droplets, nature has provided the perfect geometric form for creating organized, predictable interactions with light. The sphere is unique among three-dimensional shapes in that every point on its surface is exactly the same distance from its center. This perfect symmetry means that light rays entering the sphere from any direction encounter the same geometric relationships, ensuring that the optical processes occur with mathematical precision and consistency. Unlike irregular shapes that would scatter light unpredictably, the sphere provides a standardized optical environment where the laws of refraction and reflection can operate with clockwork regularity. When sunlight approaches a spherical water droplet, each ray of light encounters the curved surface at a specific angle determined by the geometry of the sphere and the direction of the incoming light. The curvature of the sphere ensures that parallel rays of sunlight, like those coming from our distant sun, enter the droplet at a range of angles that create the optimal conditions for both refraction and internal reflection. This range of entry angles is crucial because it provides the geometric diversity necessary for creating the full spectrum of rainbow colors. Surface tension, the force that holds water molecules together and gives droplets their shape, naturally pulls water into the most efficient form possible, a perfect sphere. This happens because the sphere has the smallest surface area of any shape that can contain a given volume of water, minimizing the energy required to maintain the surface. In the gentle conditions following a quiet storm, surface tension can operate without interference from strong winds or turbulence, allowing each droplet to achieve and maintain its ideal spherical form. The size of these spherical droplets is also crucial to their optical function. Droplets that are too small, less than about 0.1 millimeters in diameter, don't provide enough internal path length for effective color separation. Droplets that are too large, more than about 5 millimeters, become distorted by air resistance and gravity, losing their perfect spherical shape. But droplets in the ideal size range, typically between 0.5 and 2 millimeters in diameter, maintain their spherical integrity while providing the perfect optical path length for rainbow formation. The internal geometry of a spherical droplet creates a specific optical pathway that's essential for rainbow formation. When light enters the front surface of the sphere, it refracts and travels through the water toward the back of the droplet. At the back surface, a significant portion of the light undergoes total internal reflection, bouncing back through the water toward the front surface. When this internally reflected light reaches the front surface again, it exits the droplet at angles that depend on both the spherical geometry and the wavelength of the light. This internal reflection is what concentrates the dispersed colors and directs them back toward observers at specific angles. Without the curved geometry of the sphere, this focusing effect wouldn't occur, and the separated colors would scatter in all directions rather than being organized into the coherent bands that create visible rainbows. The sphere acts as both a prism to separate colors and a curved mirror to concentrate and direct those colors. The mathematical precision of spherical geometry ensures that the angle at which each color exits a water droplet is completely predictable. For red light, this angle is approximately 42.3 degrees from the direction of the incoming sunlight. For violet light, it's about 40.6 degrees. The intermediate colors fall between these extremes in perfect order, creating the systematic arrangement of colors that characterizes rainbow displays. This angular precision is what makes rainbows appear at a specific position in the sky relative to the sun and the observer. If you're looking at a rainbow, the sun is always behind you, and the rainbow appears at a specific angular distance from the antisolar point, the point in the sky directly opposite the sun. The primary rainbow appears at an angular radius of about 42 degrees from this antisolar point, while the fainter secondary rainbow, when visible, appears at about 51 degrees. The three-dimensional nature of spherical geometry also explains why rainbows appear as arcs rather than straight lines or other shapes. The droplets that contribute to the rainbow exist on the surface of an imaginary cone, with your eye at the apex and the rainbow marking where this cone intersects the curtain of suspended water droplets. If the ground didn't interfere and conditions were perfect, you would see this complete cone as a full circle of color. The curvature of spherical droplets also affects the brightness and saturation of rainbow colors through focusing effects. Just as a curved lens can concentrate light to create bright, intense illumination, the curved surface of water droplets focuses the separated colors, making them appear brighter and more saturated than they would if the same light were dispersed by flat surfaces or irregular shapes. The orientation of spherical droplets in space doesn't affect their optical properties, which is crucial for rainbow formation. Unlike crystals or other shapes that might have preferred orientations, spheres look the same from every direction. This means that water droplets falling through the air at various orientations all contribute equally to rainbow formation, creating the consistent optical conditions necessary for clear, stable rainbow displays. The transparency of water in spherical form is also optimized for rainbow formation. The spherical shape minimizes the distance that light must travel through the water while still providing enough path length for effective dispersion. This balance ensures that colors are separated clearly without being significantly dimmed by absorption during their journey through the droplet. The surface tension that maintains the spherical shape of water droplets also creates a perfectly smooth optical surface. Unlike manufactured lenses that might have microscopic scratches or imperfections, the surface of a water droplet is as smooth as physics allows, providing ideal conditions for clear refraction and reflection. This natural perfection is what gives rainbow colors their characteristic clarity and purity. The stability of spherical droplets in the gentle air following quiet storms ensures that rainbow displays can persist for extended periods. As long as the droplets maintain their spherical shapes and remain suspended in the proper positions, the geometric conditions for rainbow formation remain constant. This stability is what allows you to observe and appreciate a rainbow from your window, rather than seeing just brief flashes of color. The way that millions of spherical droplets work together to create a rainbow demonstrates the power of geometric consistency in natural phenomena. Each droplet performs exactly the same optical operations according to the same geometric principles. But droplets at different positions relative to your viewing angle contribute different colors to the overall display. The result is a systematic organization of colors that spans a significant portion of the sky. The perfection of spherical geometry also explains why artificial rainbow displays, created using water sprays from garden hoses or fountains, can closely approximate natural rainbows. As long as the water forms approximately spherical droplets and the geometric relationships between sun, droplets, and observer are correct, the same optical processes occur regardless of whether the droplets form naturally or artificially. The mathematical beauty of spherical rainbow formation has fascinated scientists and mathematicians for centuries. The precise relationships between angles, wavelengths, and colors can be calculated using relatively simple trigonometry and optics, yet they produce phenomena of extraordinary beauty and complexity. This combination of mathematical elegance and visual splendor makes rainbows unique among natural phenomena. The quantum mechanical aspects of light interaction with spherical droplets add another layer of precision to rainbow formation. At the microscopic level, photons interact with water molecules according to quantum mechanical principles that depend on the precise geometric relationships created by the spherical shape. These quantum effects contribute to the sharpness and clarity of color separation that characterizes the best rainbow displays. As you continue watching the rainbow develop outside your window, you're observing the practical consequences of spherical geometry operating on countless individual droplets simultaneously. Each sphere is performing its optical function with perfect consistency, contributing its portion of separated color to the overall display. The mathematical precision of spherical geometry ensures that all these individual contributions add up to create the organized, structured beauty of the complete rainbow. The environmental factors that preserve spherical droplet shapes, the gentle air currents, the stable temperature and pressure conditions, the absence of strong winds or turbulence, are the same factors that allow rainbow formation to proceed with optimal clarity and duration. The quiet storm that preceded this rainbow didn't just provide the water droplets. It created the atmospheric conditions that allow those droplets to maintain the perfect spherical shapes necessary for their optical function. The size distribution of spherical droplets in the post-storm air also affects the characteristics of the emerging rainbow. Larger droplets tend to produce brighter, more saturated colors but narrower color bands. Smaller droplets create broader bands but may appear less intense. The mixture of droplet sizes that typically exists after gentle precipitation creates a balanced rainbow display with both good color saturation and sufficient bandwidth for clear visibility. The refractive properties of spherical water droplets create not just the primary rainbow that's most easily visible, but also secondary and sometimes tertiary rainbows that appear at different angular positions. These additional rainbows form when light undergoes multiple internal reflections within the droplets before exiting, creating fainter displays at larger angular distances from the primary arc. As the rainbow continues to strengthen and become more defined outside your window, you're witnessing the geometric perfection of spherical droplets organizing the chaos of mixed wavelengths into the ordered beauty of separated colors. The sphere's perfect symmetry, maintained by surface tension and preserved by gentle atmospheric conditions, provides the geometric foundation for one of nature's most mathematically precise and visually stunning phenomena. In our next exploration, we'll discover how the precise angles created by spherical geometry align with the positioning of the sun and your viewing perspective to create the specific geometric conditions that make the rainbow visible from your particular window at this particular moment in time. As the rainbow begins to take more definite shape outside your window, we arrive at one of the most precise and beautiful aspects of this natural phenomenon. The moment when countless geometric relationships align with mathematical perfection to create the exact conditions necessary for rainbow visibility. This alignment involves not just the water droplets and sunlight we've been observing, but also your position as an observer, the angle of the sun in the sky, and the three-dimensional spatial relationships that must come together with clockwork precision to transform scattered light into organized bands of color. The fundamental geometry of rainbow formation depends on what physicists call the critical angle, the specific angular relationship between the incoming sunlight, the water droplets, and your line of sight that determines whether a rainbow will be visible and where it will appear in the sky. This critical angle isn't arbitrary or approximate. It's determined by the fundamental optical properties of water and the wavelength of light, calculated with mathematical precision that has remained constant since the formation of our solar system. For the primary rainbow that's developing outside your window, this critical angle is approximately 42 degrees. This means that you see rainbow colors coming from water droplets that are positioned at exactly 42 degrees away from the anti-solar point, the imaginary point in the sky directly opposite the sun from your perspective. This 42-degree relationship is so fundamental to rainbow formation that it's sometimes called the rainbow angle, representing one of the most reliable geometric constants in atmospheric optics. The precision of this angular relationship means that for you to see a rainbow from your window, several geometric conditions must align simultaneously. The sun must be behind you and at an elevation of less than 42 degrees above the horizon. The water droplets must be in front of you at the correct distance and density. Your viewing height and position must provide a clear line of sight to the region where the critical angle intersects the droplet field. Even small changes in any of these relationships can make the difference between a brilliant rainbow and no visible colors at all. The sun's position in the sky is constantly changing as Earth rotates, which means that the geometric conditions for rainbow formation are constantly shifting as well. The rainbow that's forming outside your window exists in a dynamic balance between the moving sun, the drifting droplets, and your stationary viewing position. This dynamic relationship explains why rainbows often seem to move or change shape as you watch them, and why they typically last only as long as the geometric conditions remain favorable. The height of the sun above the horizon is particularly crucial to rainbow visibility. When the sun is high in the sky, more than 42 degrees above the horizon, the geometry makes it impossible to see a rainbow because the critical angle would place the rainbow below the ground level. This is why rainbows are most commonly seen in the morning or evening when the sun is lower in the sky, or during winter months when the sun never rises very high even at midday. The azimuth direction of the sun, its position along the horizon, determines where in the sky the rainbow will appear. The rainbow always forms on the side of the sky opposite the sun, centered on the anti-solar point. If the sun is in the west, the rainbow appears in the east. If the sun is in the south, the rainbow appears in the north. This relationship is so reliable that experienced observers can predict exactly where a rainbow will appear based solely on the sun's position. Your elevation above the surrounding landscape affects how much of the rainbow you can see from your window. Observers at higher elevations can often see more complete rainbow arcs because the ground doesn't block as much of the lower portion of the rainbow circle. From an airplane or mountaintop, It's sometimes possible to see complete circular rainbows, revealing the full geometric relationship that's usually partially hidden by the Earth's surface. The distance to the water droplets that create the rainbow is another crucial geometric factor. Rainbows can appear to be very close, as near as the spray from a garden sprinkler, or very distant, involving droplets that are miles away. The key factor isn't the absolute distance to the droplets, but whether droplets exist at the correct angular positions relative to your viewing perspective and the sun's location. The three-dimensional nature of rainbow geometry creates the characteristic arc shape that's so distinctive and beautiful. The droplets that contribute to the rainbow don't lie in a flat plane, but exist on the surface of an imaginary cone extending outward from your viewing position. The rainbow arc marks where this cone intersects the field of suspended water droplets. The curvature of this intersection creates the graceful arc that spans across the sky. The width of the rainbow arc depends on the range of droplet sizes present in the air and the precision of the optical conditions. Smaller droplets tend to create broader, more diffused rainbow bands, while larger droplets produce narrower, more sharply defined color bands. The mixture of droplet sizes that typically exists after gentle precipitation creates rainbow bands that are neither too narrow to see clearly nor too broad to maintain distinct color separation. The angular width of each color band within the rainbow is determined by the optical properties of water and the wavelength dispersion that occurs during light refraction. Red light exits water droplets at slightly different angles than orange light, which exits at different angles than yellow light, and so on through the spectrum. These angular differences, measured in fractions of degrees, are what create the spatial separation between colors that allows you to see them as distinct bands. The brightness gradient across the rainbow reflects the efficiency with which different geometric relationships concentrate light. The brightest part of each color band occurs at the exact critical angle for that wavelength, where the maximum amount of light is concentrated. Moving slightly away from this optimal angle, the brightness decreases gradually, creating the soft edges that characterize natural rainbow displays. The polarization of light within the rainbow adds another layer of geometric complexity to the phenomenon. Light that has undergone internal reflection within water droplets becomes partially polarized, and this polarization varies across the width of the rainbow bands. Observers wearing polarizing sunglasses can sometimes see dramatic changes in rainbow intensity and color saturation as the polarization direction of the rainbow light interacts with the orientation of the polarizing filters. The atmospheric conditions that affect light transmission also influence the geometric precision of rainbow formation. Slight variations in air density, humidity, or temperature can create small changes in the refractive index of air, which in turn can affect the precise angles at which light travels from droplets to observers. The clean, stable air following gentle storms minimizes these effects, allowing rainbow geometry to operate with optimal precision. The alignment of rainbow geometry with human visual perception creates additional layers of beauty and meaning in the phenomenon. The angular size of the rainbow arc is well matched to human field of view, allowing observers to see substantial portions of the rainbow without having to move their heads or change their viewing position. The color progression from red to violet follows the same sequence that appears in human color perception experiments, suggesting deep connections between rainbow physics and the evolution of human vision. The temporal stability of geometric relationships during rainbow formation depends on the persistence of the atmospheric conditions that created the phenomenon. As long as water droplets remain suspended at the correct positions, the sun maintains its angular relationship to your viewing position, and the air remains clear and stable. The geometric conditions for rainbow visibility persist. Changes in any of these factors can cause the rainbow to fade, shift, or disappear entirely. The mathematical relationships that govern rainbow geometry have been studied and refined by scientists for centuries, leading to precise equations that can predict rainbow position, brightness, and color characteristics based on solar position, droplet properties, and observer location. These equations demonstrate that rainbow formation follows deterministic physical laws with the same precision as planetary motion or atomic behavior. The secondary rainbow that sometimes appears outside the primary arc results from light that undergoes two internal reflections within water droplets before exiting. This additional reflection creates a different set of critical angles, placing the secondary rainbow at approximately 51 degrees from the antisolar point, with the color sequence reversed compared to the primary rainbow. The geometric precision required for secondary rainbow visibility is even more demanding than for primary rainbows, which is why secondary rainbows are fainter and less frequently observed. The supernumerary bows that occasionally appear as faint bands inside the primary rainbow result from interference effects that occur when light waves from different parts of the same droplet interact with each other. These interference patterns depend on extremely precise geometric relationships and are visible only when atmospheric conditions and droplet characteristics are optimal. The relationship between rainbow geometry and the Earth's rotation creates subtle but measurable effects on rainbow position and visibility over time. As the Earth turns, the Sun's position relative to your location changes continuously, which means that the geometric conditions for rainbow formation are constantly evolving. The rainbow you see from your window exists within a narrow time window when all the necessary geometric relationships happen to be aligned. The spherical trigonometry that describes rainbow geometry connects this atmospheric phenomenon to the broader mathematical principles that govern celestial mechanics, navigation, and geodesy. The same mathematical tools used to calculate planetary orbits or global positioning coordinates can be applied to rainbow prediction and analysis, demonstrating the universal nature of geometric relationships in physics. As you continue watching the rainbow strengthen and stabilize outside your window, you're observing the practical result of these precise geometric alignments operating in real time. Every element of the rainbow's position, shape, and color characteristics reflects the mathematical relationships between angles, wavelengths, and optical properties that govern this natural phenomenon. The beauty of rainbow geometry lies not just in its mathematical precision, but in the way this precision creates visual experiences of extraordinary beauty and meaning. The same angular relationships that can be calculated with mechanical precision produce phenomena that have inspired art, poetry, and spiritual reflection throughout human history. The intersection of mathematics and beauty in rainbow formation demonstrates that the universe operates according to principles that are both rationally comprehensible and aesthetically sublime. In our next exploration, we'll witness the culmination of all these geometric relationships as the individual color contributions from millions of precisely positioned droplets combine to create the visible rainbow arc that's about to span the sky outside your peaceful window, marking the emergence of organized beauty from the chaos of scattered light and suspended water. As we reach this pivotal moment in our gentle observation from the window, we're about to witness one of the most magical transitions in all of natural phenomena. The moment when countless individual interactions between light and water droplets reach the threshold where they combine to create something greater than the sum of their parts. The rainbow that has been building through the precise alignment of angles, the separation of wavelengths, and the optical perfection of spherical droplets is about to emerge as a visible, coherent arc of color spanning across the sky. The transition from invisible to visible rainbow represents a fascinating example of what scientists call an emergent phenomenon, a situation where many small, individual events combine to create something that appears suddenly and dramatically different from its components. Each water droplet has been performing its optical function throughout our observation, separating white light and redirecting colors at specific angles. But only now, as enough droplets become optimally positioned and illuminated, do these individual contributions reach the critical mass necessary for human perception. The threshold of visibility is remarkably precise, determined by the sensitivity limits of human vision and the concentration of colored light that must be achieved before our eyes can distinguish rainbow colors from the background illumination of the sky. This threshold explains why rainbows often seem to appear suddenly, even though the optical processes that create them have been building gradually. One moment the sky shows only subtle hints of color, and the next moment a complete arc of distinct bands stretches across the heavens. As more sunlight breaks through the clearing clouds outside your window, illuminating additional regions of the suspended droplet field, you begin to see the first definite traces of the rainbow arc taking shape. It might start as a faint reddish glow in one section of sky, gradually extending and brightening as more droplets in the optimal geometric positions become involved in the light scattering process. The emergence isn't uniform but progresses along the arc as conditions optimize in different regions of the droplet field. The three-dimensional nature of rainbow formation becomes evident as the arc develops. Unlike a painted rainbow that exists on a flat surface, this natural rainbow has depth and dimension, created by droplets at various distances from your viewing position. Droplets closer to you contribute to one part of the arc, while droplets farther away contribute to other parts, creating a complex, layered structure that gives the rainbow its distinctive appearance of floating in space. The brightness gradient across the developing rainbow arc reflects the varying efficiency with which different regions concentrate colored light. The brightest parts of the arc occur where the geometric conditions are most favorable, where the largest number of optimally sized droplets are positioned at exactly the right angles relative to the sun and your viewing position. These bright regions often appear first and most clearly, gradually extending as conditions improve in adjacent areas. The color sequence that emerges follows the inevitable order determined by the wavelength-dependent refraction that occurs in water droplets. Red appears on the outer edge of the arc because red light exits droplets at the largest angle from the incoming sunlight direction. Violet appears on the inner edge because violet light exits at the smallest angle. The intermediate colors, orange, yellow, green, blue, indigo, arrange themselves between these extremes in the precise order determined by their wavelengths and refractive properties. The width of each color band in the emerging rainbow depends on the range of droplet sizes present in the air and the precision of the atmospheric conditions. In the clean air following a gentle storm, with uniform droplet sizes and stable atmospheric conditions, the color bands appear crisp and well-defined. Each color occupies its designated angular space with minimal overlap or confusion, creating the clear color separation that characterizes the most beautiful rainbow displays. The saturation and intensity of the colors depend on multiple factors working together: the purity of the water droplets, the clarity of the atmosphere, the angle and intensity of the sunlight, and the density of optimally positioned droplets. The gentle storm that preceded this rainbow has optimized all these factors, creating conditions where colors appear with exceptional purity and brightness. The red band glows with warm intensity. The green appears vivid and natural. The blue and violet show the deep, rich tones that make rainbow displays so memorable. The mathematical precision of rainbow formation becomes evident as the arc develops its characteristic shape and proportions. The radius of curvature is determined by the 42-degree critical angle and your viewing height above the landscape. The angular width of the arc depends on how much of the rainbow circle is visible above the horizon. The spacing between color bands follows the wavelength dispersion characteristics of water. Every aspect of the rainbow's geometry can be calculated and predicted with the same precision as any other optical phenomenon. The background provided by the sky and clouds plays a crucial role in rainbow visibility. The dark storm clouds that are moving away provide the perfect contrast against which the rainbow colors can be seen clearly. Without this dark background, the colored light would be present but invisible against the bright sky. The timing of rainbow emergence often coincides with the optimal balance between sufficient sunlight to illuminate droplets and sufficient cloud cover to provide contrast. The polarization characteristics of rainbow light become apparent as the arc reaches full visibility. The light that creates rainbow colors has been partially polarized by its interaction with water droplets, giving it a distinctive quality that's different from ordinary skylight. This polarization can make rainbow colors appear to shimmer or change intensity slightly as you move your head or shift your viewing angle, adding a dynamic quality to the static arc. The atmospheric optics that create the rainbow also produce subtle secondary effects that enhance the overall display. The region between the primary rainbow and the secondary rainbow, when visible, often appears darker than the surrounding sky, a phenomenon called Alexander's dark band, named after the ancient Greek philosopher who first described it. This darkening occurs because the geometric constraints of rainbow formation create a zone where less scattered light reaches observers. The temporal evolution of the rainbow arc reflects the changing atmospheric conditions as the storm system continues to move away and sunlight becomes stronger and more consistent. The rainbow may start as a partial arc and gradually extend as more regions of the droplet field become optimally illuminated. Alternatively, it might appear as a complete arc that gradually brightens and becomes more defined as conditions continue to improve. The stability of the rainbow arc depends on the persistence of the atmospheric conditions that created it. In the gentle, stable air following a quiet storm, rainbows can persist for 30 minutes or more, providing extended opportunities for observation and appreciation. The lack of turbulence means that droplets maintain their optimal positions and shapes, while the gradual clearing of clouds provides consistent illumination conditions. The human perception of rainbow emergence involves both physiological and psychological factors that enhance the impact of the phenomenon. The human visual system is particularly sensitive to the types of color contrasts and brightness patterns that characterize rainbows, making them appear more vivid and striking than their actual light intensity might suggest. The brain's pattern recognition systems also contribute to rainbow perception, helping to organize the colored light into the coherent arc structure that we recognize as a rainbow. The cultural and emotional significance of rainbow emergence adds layers of meaning to the optical phenomenon. Throughout human history, rainbows have been interpreted as signs of hope, promises of better weather, bridges between earth and sky, or symbols of peace and renewal. These associations, developed through countless generations of human experience with post-storm weather, contribute to the emotional impact of witnessing a rainbow's emergence. The photographic challenges of capturing rainbow emergence highlight the unique optical characteristics of the phenomenon. Rainbows often appear much fainter in photographs than they do to human eyes because cameras don't share the visual sensitivity and processing capabilities that make rainbows so vivid to human perception. The dynamic range of rainbow light, from the bright bands to the subtle gradations between colors, often exceeds what camera sensors can capture effectively. The scientific study of rainbow emergence has contributed to broader understanding of atmospheric optics, light scattering, and human color perception. Rainbow research has informed the development of optical instruments, helped refine theories of electromagnetic radiation, and provided insights into the physics of water droplets and atmospheric phenomena. The precise mathematical relationships governing rainbow formation have served as test cases for optical theories and computational models. The emergence of the rainbow arc outside your window represents the culmination of all the physical processes we've been exploring. The gentle storm that created perfect droplets, the clearing skies that provided optimal lighting, the precise geometric relationships that aligned sun, droplets, and observer, and the wavelength separation that organized white light into its component colors. All these factors have combined at exactly the right moment to create the threshold conditions where individual optical events become a collective display of extraordinary beauty. The rainbow that's now spanning across the sky demonstrates the power of natural processes to create phenomena that are both scientifically explainable and aesthetically overwhelming. The same laws of physics that govern the behavior of individual photons and molecules have produced a display that connects Earth to sky in an arc of pure color, visible for miles and inspiring wonder in all who witness its emergence. As the rainbow reaches its full development, with all colors clearly defined and the arc extending across a significant portion of the sky, you're witnessing one of nature's most perfect demonstrations of how simple physical laws, operating through countless individual interactions, can create phenomena of breathtaking beauty and mathematical precision. The emergence of the arc marks not just the visibility of separated light, but the revelation of the hidden order and beauty that underlies the everyday interactions between sunshine and water. In our next exploration, we'll discover how each color finds its specific place within the rainbow arc, creating the organized progression from red to violet that has captivated human observers since the first humans looked up at the sky after storms and witnessed this eternal dance between light and water. As the rainbow reaches its full glory outside your window, with the complete arc now visible in all its colorful splendor, we arrive at one of the most beautiful and orderly aspects of this natural phenomenon. The way each color finds and maintains its exact place within the spectrum, creating the organized progression from red through orange, yellow, green, blue, indigo, to violet that has remained constant throughout all of human history. This ordering isn't random or accidental, but represents the direct visual manifestation of fundamental physics principles governing how light interacts with matter. The sequence of colors in every rainbow follows the same pattern because it's determined by the immutable properties of electromagnetic radiation and the consistent optical characteristics of water. Red light, with its longer wavelengths of approximately 700 nanometers, undergoes the least amount of bending when it enters and exits water droplets. This minimal refraction means that red light emerges from droplets at the largest angle relative to the incoming sunlight, positioning it on the outer edge of the rainbow arc where it glows with warm intensity against the dark backdrop of retreating storm clouds. Orange light, with wavelengths around 620 nanometers, bends slightly more than red as it passes through water, causing it to emerge at a correspondingly smaller angle and positioning it just inside the red band. The orange appears as a warm bridge between the robust red and the brilliant yellow, carrying wavelengths that our eyes perceive as the color of autumn leaves, sunset skies, and glowing embers. In the rainbow outside your window, orange maintains its position with mathematical precision, neither crowding into the red space nor encroaching on the yellow territory. Yellow light, at wavelengths near 580 nanometers, occupies a special place in both the rainbow spectrum and human visual perception. Yellow sits near the peak sensitivity of human vision, which evolved to be most responsive to the wavelengths that are most abundant in sunlight after it passes through Earth's atmosphere. In the rainbow arc, yellow appears with particular brilliance and clarity, often seeming to glow with its own inner light as it takes its designated position between the warm oranges and the cooler greens. Green light spans a range of wavelengths from about 500 to 570 nanometers, making it the broadest band in the visible spectrum and often the most prominent color in rainbow displays. Green light bends more than the warmer colors as it passes through water droplets, positioning it in the central portion of the rainbow arc. The green band often appears particularly vibrant and natural, reminiscent of spring foliage, growing grass, and the countless green things that define the living world around us. Blue light, with wavelengths around 470 nanometers, undergoes significant bending as it travels through water droplets, causing it to emerge at angles that position it well inside the rainbow arc, between the greens and the violets. Blue light has traveled a complex journey to reach your eyes, having been scattered multiple times by atmospheric molecules, the same scattering that makes our sky blue on clear days. In the clean air following gentle storms, blue light appears with exceptional clarity and depth, creating bands of color that seem to echo the infinite depths of clear skies. Indigo, with wavelengths around 445 nanometers, occupies a narrow band between blue and violet that's sometimes difficult to distinguish clearly, but adds depth and richness to the overall spectrum. Indigo represents light that's undergoing near maximum refraction in water droplets, bending sharply as it enters and exits the spherical surfaces. The presence of distinct indigo depends on optimal atmospheric conditions and the precise size distribution of water droplets, making it a mark of particularly perfect rainbow displays. Violet light, at the short wavelength end of the visible spectrum around 380 to 420 nanometers, undergoes the maximum amount of bending in water droplets and emerges at the smallest angles relative to incoming sunlight. This positions violet on the inner edge of the rainbow arc, where it appears as a band of deep, rich purple that seems to vibrate with energy. Violet light carries the highest energy per photon of any visible light, and its position at the inner edge of the rainbow marks the boundary between visible light and the ultraviolet radiation that lies beyond human perception. The boundaries between these colors are not sharp lines, but gentle gradations that reflect the continuous nature of the electromagnetic spectrum. There are no gaps in the wavelengths that make up sunlight, so there are no gaps in the rainbow colors. Instead, each color blends smoothly into its neighbors, creating subtle transition zones where orange gradually becomes yellow, where green slowly shifts to blue, where blue imperceptibly transforms into violet. These gradual transitions are part of what makes rainbows so visually appealing and naturally harmonious. The relative brightness of different colors in the rainbow reflects both the energy distribution in sunlight and the sensitivity characteristics of human vision. Yellow and green often appear brightest because they correspond to the peak of both solar energy output and human visual sensitivity. Red may appear less intense than yellow, but often seems to glow with warmth and depth. Blue and violet, despite carrying more energy per photon, may appear dimmer because human eyes are less sensitive to these shorter wavelengths, and because these colors are more susceptible to atmospheric scattering. The width of each color band depends on the wavelength range that our visual system groups together as a single color category. Green, covering the broadest range of wavelengths, often appears as the widest band in rainbow displays. Red and violet, representing the extremes of visible light, may appear as narrower bands that fade gradually into invisibility at their outer edges. The intermediate colors, orange, yellow, blue, indigo, typically appear as bands of moderate width that provide smooth transitions between the primary colors. The saturation and purity of rainbow colors depend on the optical quality of the water droplets and the clarity of the atmospheric conditions. In the ideal conditions following gentle storms, with pure water droplets and clean air, rainbow colors appear with exceptional saturation, meaning they're free from white light contamination and appear as pure, vivid hues. This purity is what distinguishes natural rainbow colors from artificial displays, which often suffer from imperfect color separation or atmospheric interference. The psychological impact of the color progression from red to violet connects rainbow viewing to deep aspects of human color perception and emotional response. The warm colors, red, orange, yellow, often evoke feelings of energy, warmth, and comfort. The cool colors, green, blue, violet, may suggest calm, peace, and tranquility. The complete spectrum provides a visual journey from warm to cool that many observers find emotionally satisfying and aesthetically complete. The cultural significance of rainbow color ordering has influenced human art, design, and symbolism for millennia. The consistent sequence of rainbow colors has provided a natural standard for color organization that appears in everything from artistic compositions to scientific instruments. The acronym ROY-G, BIV, red, orange, yellow, green, blue, indigo, violet, has helped countless students remember the rainbow sequence, demonstrating how natural phenomena can provide organizing principles for human knowledge. As our gentle journey through the science and beauty of rainbow formation draws toward its peaceful conclusion, we find ourselves resting in the contemplation of this perfect moment outside your window, where all the elements we've explored have come together to create one of nature's most reliable yet miraculous displays. The rainbow that now spans across the sky represents the culmination of countless gentle processes, the quiet storm that created perfect droplets, the emerging sunlight that provided pure illumination, the precise geometry that aligned all the necessary angles, and the fundamental physics that organized chaos into beauty. As you settle more deeply into your comfortable spot by the window, watching this arc of color stretch across the heavens. You're witnessing something that connects you to every human who has ever looked up at the sky after rain and felt wonder at the sight of organized light painting itself across the atmosphere. This rainbow exists in this moment, visible from your particular vantage point, yet it embodies principles and processes that are as universal and eternal as the laws of physics themselves. The rainbow's gentle presence speaks to the profound harmony that exists in natural processes when conditions align in just the right way. There was no violence in its creation, no force or struggle, just the patient interaction of water and light following the same laws that have governed such interactions since the first rains fell on the first sunlit days in Earth's history. The quiet storm whispered rather than roared, creating the perfect conditions for this display of organized beauty to emerge from apparent randomness. As evening approaches and your eyelids grow heavy, let the peaceful presence of the rainbow outside your window guide you toward restful sleep. The colors that dance across the sky carry within them all the gentle science we've explored together. The perfect spheres of water, the hidden symphony of wavelengths in sunlight, the mathematical precision of angles and reflections, the emergence of order from countless individual interactions. Sleep peacefully, knowing that the same natural laws that create rainbows operate throughout the universe with reliable constancy, that beauty and order emerge naturally from the fundamental structures of reality, and that tomorrow's gentle storms may bring their own gifts of light and wonder. Thank you for joining me on this peaceful exploration of rainbow science. If these gentle journeys into the hidden workings of our natural world have brought you comfort or wonder, I'd be grateful if you'd consider subscribing to Whispering Atom and sharing your thoughts in the comments below. Where in the world are you drifting toward sleep tonight? And what aspects of rainbow formation spoke most peacefully to your mind? Until our next gentle exploration together, may your dreams be as beautiful and harmonious as the colors that arch across the sky after the quietest storms, and as peaceful as the whispered science that reveals the hidden order in our extraordinary natural world.